2:30.
That's not good.
Yeah.
Because we're most likely not going to finish by 2:30. Yeah. A lot to cover today. So let's start with recap of where we left off. So once again, we're always talking about sample spaces. Let's start with that. What's a sample space?
The given elements in their probability.
Yeah, it's the set of all possible outcomes and the probability of each of them, right? So we have a set and a function. We know some special things about that function. What's the domain of the function? It's S is the domain of the function. What's the minimum right-hand value a particular value can have? 0. And what's the maximum it can have? 1. And the sum of all the probabilities is 1. So that's what you know. We're out the door when you have a sample space. Then we talked about an event. What was an event?
It's a subset of that.
It's just a subset of S. It's all an event is. Subset of S. Okay? And the way that you calculated a probability of an event is for each element in S, calculate its individual probability and then sum all those up. That's your probability of a particular event. All right. So today we're going to introduce another concept which it feels weird the first time you come across it. It's called a random variable. And this is not a variable in the sense that you're used to. It's a function. It's a function whose domain is S. Okay? Now, we use random variables to capture useful information from a particular sample space. So let's look at some example sample spaces that we're already used to, and then some random variables that we might want to define.
What is
Any set. It's a set from S to anything. That could be to sets of other sets. That could be the real numbers. That could be anything. Any other set. So we don't have any information about B. It's just a random variable is a function from S to some set. We don't restrict it. So once again, a lot of room to choose how you want to do it. Right? The same way that there's no right way to set your sample space, there's no, this is a random variable you should use and how you should define it. The only requirement is the domain is S. Okay? So let's go through some examples and set some random variables that might be useful. So, one that we like is the sample space for rolling a pair of dice, right? The set of all possible outcomes, it makes sense to represent it as the set of all the ordered pairs from that Cartesian product, right? Remember, that's not the S we had to use. One of the examples I gave you was I drew like a picture of each of the dice. That's perfectly valid too. This one we chose to use numbers. Perfectly valid. So S will make the Cartesian product of those. We'll assign a probability of 1/36 to each outcome, right? Just what you'd expect. And something that we might be interested in is what the dice sum up to. So we might make a random variable x that gives us the sum of the dice. So it takes 1, 1 and maps it to 2. It takes 2, 3 and maps it to 5. It takes 4, 5 and maps it to 9. You with me? So in this case, it's just mapping from S to real numbers. And it's just giving us a sum. That might be something that we want to know, so we might define this function to give us a sum. Good with me so far? Nothing weird? Alright. Another example. So let's have SP be the sample space for 10 coin tosses. So S equals, you remember when we came up with the notation for raising this to power? It was all the length 10 lists we could make using these as the elements.
Oh, great.
Remember that? So an element in S is a length 10 list of H's and T's. That's what S is. And then the probability of each of those outcomes, we're just going to make it each one equally likely. So it's just 1 over 2 to the 10, or 1 over 10 to, or 1024. Good with that? Okay, So then we might arbitrarily decide, let's make a random variable that tells us how many heads are word minus how many tails are word. So we'll make x that random variable. So x, if you were to give it this list as its input, it would spit out -2. Why? Because there's 4 heads and 6 tails in that string. -2. Yeah?
Yeah, that's interesting.
Just random. Let's make another random variable. We'll say that this one gives you the positions of the heads. So when you give it that exact same string, it spits out set 1, 2, 4, 6. Maybe that's what you care about.
So, which part is the random variable?
This is a random variable, and this is a random variable.
I'm saying like,
The random variable is the function.
so that's.
This is just showing a particular value. Because if we were to write out the whole function, then it's going to be massive.
What? I'm saying the random variable is the sentence, correct?
The random variable is the function. X is a random variable.
Right.
Z is a random variable. They're both random variables. They're both functions whose domain is this thing. And that's all. That's the only requirement. This one, we decided to pick this one to capture this information. And we decided to pick this one to capture this information. Right? The same way that you choose your probabilities to try and capture the likelihood of something happening. It's kind of the same way that we picked events. You came up with some random event in a way of capturing it. It feels weird when you first get to it, but when you see where we use it, then you'll see why it's useful. So let's continue to another one. So once again, let's have SP for a pair of dice. Use the same one that we had here. And let's make an event that we're used to. Let A be the event we ruled in 8. What does A equal? It equals this set right here. That's the event ruled in 8. Right? Now, rather than making events for all the possible rules that we have, making an event for rolling a 2, making an event for rolling a 3, making an event for rolling a 4, that's pretty tedious to do. So this is the old way of doing it. Now, instead, let's create a random variable. Let x be the random variable that gives you the sum of the rolls. So if you get 2, 3, if you give it 2, 3, x spits out 5. And in general, if you give it a, b, x spits out a plus b. You with me? So now, instead of asking, what's the probability of event A, which is we rolled an 8, which we know how to calculate, we can just say, what's the probability that x equals 8? Which is the same thing.
So.
You're good with A is this event.
Yeah.
Okay. X is just a function that spits out the sum of the die. It tells you what you rolled, basically, right? You give it a 2 and a 3, it spits out a 5. That's what we're defining x to be. X is a function. Remember, it's a function. You give it a rule, and it spits out the value of the rule. You give it a 2 and a 3, it says, oh, you rolled a 5. You give it an a and a b, and it says, oh, you rolled a plus b.
Okay.
That's what x
How
is.
does that connect to either one of them? That makes perfect sense.
Okay,
but
so
it's-
now instead of saying what's the probability of event A, which is ruled in 8, and we know how to calculate that, right? There were 5 ways we could roll in 8. Each of them are equally likely. The probability of rolling in 8
Now
is
you're
just
saying what's
536.
the probability of x equaling 8?
Yeah, so now instead of having to come up with this particular event and then saying what's the probability of that event,
Huh.
we have x equals the outcome of the die. That's what we really care about. And now we just ask what's the probability that x will be 8.
Isn't that harder though?
It's harder up front. You're thinking about like writing this down on a piece of paper and
I'm
writing
saying
it out. But if
you
I
still
were
have to think about it.
if I were writing a program,
Just as much.
I don't want to write an event A for rolled in 8, an event B for rolled in 9, an event C for rolled in 10, an event D for rolled in 11. I just want to write a function function x that gives me the rule of the dice. That's what I care about. Okay, maybe that wasn't good to say. Okay, so now we said, what's the probability of rolling a 7? How are we going to do that?
Oh, I see.
You see? So now instead of saying, okay, what's the probability of rolling a 7? Instead of us going and creating an event B called rolling a 7, finding out what elements are in event B, and then calculating its probability, all we need to ask is, what's the probability that x equals 7? So now we have a faster way of asking our question, and a shorthand way for asking our questions. You see that? Okay, that's where a random variable becomes useful. So we don't have to keep defining all these events over and over again. That's not where it becomes useful, that's one way it becomes very useful. So let's continue with it. So let's go to, we got our sample space for tossing a coin 10 times, the same sample space that we had right here. Let x sub h be the random variable that gives us the count of heads. So when you give it this list, it tells you 3. Let xt be the count, x sub t be the count of tails. So when you give it the same list, it spits out 7. With me so far? Okay. What is the probability of at least 4 heads and 4 tails? So you got a coin, you're going to flip it 10 times. What is the probability that in your 10 flips, at least 4 of them are heads and at least 4 of them are tails? Do you understand the question? Let's make sure you understand the question, then we'll go over the math to capture it. You've got a coin, you're going to flip it 10 times. What's the probability that you have at least 4 heads and at least 4 tails?
0.
No.
10 times.
You flip it 10 times. What's the probability you have at least 4 heads and at least 4 tails? That's our question. Does the question make sense?
Yes.
And it makes sense that the answer isn't 0.
Right.
Okay. So here's a couple ways that we can ask that question. We say, what's the probability that x sub h is greater than or equal to 4 and x sub t is greater than or equal to 4? Right? What's the probability that our number of heads is greater than or equal to 4 and our number of tails is greater than or equal to 4? That's one way you can think about it.
Okay, wait. Why x sub h and x sub t?
X is the convention for a random variable, a capital X. And x sub h is just, it's a name I'm just choosing. The same way that I can choose whatever letter I want to call a function.
So,
I can use an f, g, h, x sub h.
so why not just say let x be the count of heads and let y be the count of tails?
I could have done that just as well. I thought x sub h and x sub t were clear. More clear. Okay, so we just have 2 random variables, x sub h, x sub t. This one gives you the count of heads in a particular string of 10 tosses. This one gives you the count of tails in a particular string of 10 tosses. We want to know the probability that in 10 flips, at least 4 of them will be heads and at least 4 of them will be tails. There's a few different ways that we can think about this question. We can think about that's the probability that the number of heads will be greater than or equal to 4, and the number of tails will be greater than or equal to 4. That's one way you can think about it. Another way you can think about it is if you think about this as a set of all outcomes that give you heads greater than or equal to 4, and this as a set of all outcomes that give you tails greater than or equal to 4. You can think about it as their intersection and then calculate the probability of that. You understand what I'm saying here? That's another way to think about it. Those two are very similar. You can think about it this way. What's the probability that our count of heads is in between 4 and 6, right? Because if it's always less than or equal to 6, then that means there's always at least 4 tails. And if it's always greater than or equal to 4, that means there's at least 4 heads. You see how this is capturing the same information here and here?
Right, yeah.
This isn't meant to help us solve this particular problem. We're just using a simple case to show you a bunch of different ways to think about it. So on your individual problems.
Yeah, that makes perfect sense.
you can start thinking about tips and tricks to help you come up with a good way to think about it. Or you can think about it this way. You can think about it as a probability that the number of heads is 4, or the number of heads is 5, or the number of heads is 6. Because the number of heads is 4 tells us 6. The number of heads is 5 tells us 5. The number of heads is 6 tells us 4. You good?
Yeah.
So, a few different ways that we can think about this problem to try and solve it. I wrote this one right here because that one was the shortest way to write it. But let's think about it this way. So, we're calculating the probability. How many of our coin flips have exactly 4 heads? How many ways can I get exactly 4 heads in 10 flips?
Exactly 4. 6 to the power of 2. Or 2 to the power of 6.
I've got 10 flips. I need to choose 4 of them to be heads.
Okay. I guess, yeah, that makes sense.
10 choose 4. That's how many will have exactly 4 heads. Plus 10 choose 5 will be how many have exactly 5 heads. Plus 10 choose 6 will be how many have exactly 6 heads. And they're all equally likely, so just divide over this. Does the division part make sense? Here. Remember, we're calculating the probability. So here's how many ways
Oh yeah, that makes sense.
we can get 4 heads and at least 4 heads and at least 4 tails, right? Now we need to calculate the probability. So we need to times it by the probability of each of those outcomes. Remember, the probability of one outcome is this. So we're going to multiply by 1 over 1024. So does that make sense for the probability? The numerator is, this is how many ways we can get exactly 4 heads, this is how many ways we can get exactly 5 heads, this is how many ways we can get exactly 6 heads. So this whole thing is, how many ways we can get at least 4 heads and 4 tails. And this is how many ways we can flip. How many ways we can get 4 heads, 4 tails, how many ways we can flip, here's the probability. Since they're all equally likely. Is there something I'm saying wrong?
Actually, how are they all equally likely?
Every outcome of a 10-string coin flip, I said, has a probability of 1 over 1024.
You see what the top and the bottom are, like what the numbers mean. But I'm not understanding why you're dividing.
Okay, let's think about this. What's the odds I flip a heads? 50-50. How many ways can I flip a heads?
1 way.
How many possible outcomes are there?
There's 2.
So 1 out of 2 ways gives me what I want.
Okay.
So this many out of this many ways gives me what I want.
Okay.
Did that click it?
Yeah.
Now that's intuition for this equation. Here's how you should think about it though. These are all the ways that give me my outcome. Each outcome is this likely. Therefore, the probability is this many times this likely.
All right.
So that's the way to think
That's
about
the
it.
way we should think about it.
We want to think about it as count times probability, because that's going to be useful for what comes up next.
Yeah.
Okay. So now, let's go back to our example with an unfair coin, and then we're going to get to a general idea for binomial probabilities. So, let SP be a sample space for an unfair coin, where the probability of heads is just some number p between 0 and 1. Yeah. And let's let x be the number of times we see a heads. Okay? So the same thing that x of h was over here. The number of times we see a heads in a particular flip. So we have an unfair coin, so it's not 50-50 anymore. And x is the number of times we see a heads. Good so far? Okay. If we toss the coin n times, What is the probability that we'll see heads exactly h times, where h is some integer? That's what we're going to calculate.
What?
So I've got the coin, it's an unfair coin. I'm going to flip it n times. Good so far?
Yeah.
I just want to calculate the probability that exactly 8 of those flips are heads. So for example, I could flip the coin 12 times and calculate the probability that 7 of them are heads. You with me? I want to do it more in general. So up here we calculate the probability that exactly 4 were heads, or exactly 5 were heads, or exactly 6 were heads in 10 coin tosses, right? I want to come up with a formula for calculating the probability that each of them will be heads in n tosses.
N choose H over.
It's going to be a sum, isn't it?
Almost. You're assuming a 50% chance. So let's continue with it. You got good intuition. Stick with your intuition. It's not a fair coin.
It's going to be
What does that mean? What's an
It means that they're not all equally likely. Anyways, let's just go through the steps here and we'll quick as we go. So first off, how many flips with exactly h heads?
Huh? How many flips with H heads?
Oh, sorry. Let's have some side conversation real quick. So I first needed to just make sure you guys understood the question. So you understand we're trying to calculate the probability of exactly h heads in n tosses, right? Where h is just some integer. Now, first off, now, if h is less than 0, or if h is greater than n, then the probability of getting that many heads is 0. The probability of me flipping 11 heads, if I only have 10 tosses, is 0. The probability of me flipping -2 heads is 0. Okay? So h has to be bounded between 0 and n. Wow, okay. So, assuming h is bounded, how many flips with h heads? With exactly h heads?
Is it P choose H?
P is some number between 0 and 1. It's a
Sorry,
probability.
N choose H.
N choose h,
Sorry.
right? I have n coin tosses, and I need exactly 8 of them to be heads. Now, why did we go through all that conversation about h isn't less than 0 and h is greater than n? So that this is defined.
Right.
So that is how many coin flips have exactly 8 heads. In other words,
It's not.
let's look at an example.
Okay.
If
How
I
many
am flipping a
flips?
coin 10 times,
How many flips?
n.
Are you asking flips or how many heads? Does N choose H?
Sorry,
Does it
I
heads?
know that my flips is a little ambiguous here because
And
you
it
think
says
about.
flips.
So let's go back up here. When I had 10 flips and I wanted exactly 4 of them heads, how many, if I'm flipping 10 times in a row, how many of those outcomes have exactly 4 heads? 10 choose 4, right? Same exact thinking.
Makes sense. Yeah.
I need to choose h of my n flips to be heads. I have n flips, choose h of them to be heads. That's how many
Wait.
have h heads in them.
That did not make sense what you just said.
So, sure.
That made that even.
I have 10 flips.
You have N flips and you want H of them to be heads.
Yeah, I have n flips. I want h of them to be heads.
Yeah.
Are we all on the same page? This is like really abstract but really simple.
Yeah.
So hard to wrap your head around until it clicks, and it's really simple and you just get it.
Well, yeah.
So let's make that connection, because if it doesn't just feel obvious now, we need to keep going over it. Because it's not a hard idea, right? I have n
Right,
flips,
that makes sense, right?
choose h of them to be heads, and choose h. That's how many ways I can have n coin tosses and exactly h of them heads. Good? All right, what is the probability of one of those particular outcomes? Let's come up with numbers for a second. Let's say that n is equal to 6 and h is equal to 3. What is the probability?
Oh, wait, no. H.
What is the probability that I get this one? H tells, H tells. What's the probability that I get that one exactly right there?
1 over.
What's the probability of H? This H. No, P.
1/6.
It's not a fair coin. The probability of getting your heads is P. So we've got P times, the probability of that one is P times, what's the probability of that one? 1 minus P. Probability of that one? 1 minus P times 1 minus P. That's the probability of getting this exact outcome, right?
Right.
What about this one? What's the probability of getting that outcome?
Be the same.
Same thing. They're all going to be P to the number of times you want heads times 1 minus P to the number of times you don't want heads. You with me?
Yeah.
So now, how many of these arrangements can I get?
2 to the 6.
No, how many, how can I say this right? How many ways can I flip my coin 6 times and have exactly 3 heads?
3 out of 6. 1 half. I don't know.
How many ways?
Oh, 6 choose 3.
6 choose 3 for the log, thank you. So this is how many ways I can have exactly 3 heads. And the probability of each of those is P to the 3, 1 minus P to the 3.
Right.
So this is the probability that x is equal to 3, right?
All right. Yeah. Yeah.
Now, back to in general.
And just substitute it in.
The probability of a particular outcome is P to the h times 1 minus P to the n minus h, right?
Right.
Sorry if my n's and h's look very similar. And so finally, calculating the probability here is n choose h times P to the h, 1 minus P to the n minus h.
Right.
Wow.
So there's our generic formula. And notice this has nothing to do with coin tosses necessarily. Coin toss is just an example. Anytime I'm asking you to calculate a probability, and the probability can be broken up into successes or failures, then I can ask you the question, what's the probability of having exactly h successes in n tries if the probability of success is some percentage?
All right.
Now you can calculate right out the door.
Yeah, that's pretty.
Easy peasy, lemon squeezy. This is exactly the kind of stuff you start with if you've ever taken probability and statistics class. This is lecture 1.
I would be so confused.
Random variables, they're really confusing the first time you come across them, and then so continuing from there on out.
Well, they make a little more sense because you've gone over events and sample space and all that. Right?
Yeah, and luckily when you do discrete math, you get to really drag out the beginning so that you can slowly make it make sense. Like taking probability statistics before you take discrete math, it's a tough class. So for a lot of people in their majors, it's the hardest class they ever take. Let's see where we're
Is there another way of coming up with that equation that doesn't involve like this example? Or is it?
coin tosses?
Well, I'm just noting that the way that we came up with this is you wrote HHT, THT, and you said what's the probability that we found that. And I'm wondering, was there a different way to think about it that would have helped you come up with it?
A different way to think. Well, it's just, I mean, you just need any specific example of successes and failures. That's what generically captures. Let P be the probability of a success, then 1 minus P is the probability of a failure, calculate exactly some number of successes. All right. So now let's write this out exactly. Where's the capital N come from? Oh, that's all they're saying. So they're saying in this context, we don't just call X a random variable, we call X a binomial random variable when it's calculating these successes and failures like this. The reason that we call it a binomial random variable is because of this exact fact right here. If you look at the binomial formula for P's and Q's instead of X's and Y's, because why not? The binomial formula, when you expand it out, is exactly this. If I replace my Q with 1 minus P, it's exactly this. Right? And now this was calculating a particular term in here. You with me? And just to make sure that you're fully wrapping your head around this, what does this sum equal?
Like expanded.
1.
Wow. Oh, right, yeah.
If Q is equal to 1 minus P, if Q is equal to 1 minus P, then that's true.
Okay.
And instead of thinking about it this way, just come right back over here. P plus 1 minus P is 1. 1 to the power of n is 1. Yeah, it's 1. Right? But over here, it should make sense this way too. Because here, what are we saying? What is the probability that you'll have either 1 success or 2 successes or 3 successes or 4 successes or 5 successes or n successes? It's going to be 1. You're going to have some number of successes. I guess you could start at 0, sorry. Binomial formula starts at 0, not 1. Does it make intuitive sense why thinking about this in terms of probabilities comes out 1?
Yeah.
And then obviously just doing the algebra here, you see it comes out 1, but that connection is an important connection to make. Because now, when I ask you to calculate some number of successes, let's say if I wanted to calculate 3 or 4 or 5 successes, you just need to come in here, figure out what the third term is, what the fourth term is, what the fifth term is, do the math on those, and you're done. All right. So that's it for binomials for now. Now let's move on to independent random variables. Now you remember that we had the idea of 2 events being independent. Do you remember how we calculated that?
Yeah.
What was it?
Are they being independent?
Yeah, how did we know that events A and B were independent of each other?
It was the probability of A intersect B equals probability of A times probability of B.
Perfect. And you'll remember the way that we derived this equation was we said that the probability of A given B is equal to if this comes out to the probability of A. If this is true, then it's true. And then this formula is the probability of A intersect B over the probability of B.
Right.
So if that is equal to PA, then that same thing as this.
Right.
So if that's equal or that's equal or that's equal, then the two events are independent. Now we'll be talking about a similar idea for two random variables being independent. So let's set up a case where they're independent.
If they're functions, that doesn't make a lot of sense.
Kind of. You'll see how it does. So let's have let SP for rolling two dice, rolling pair of dice. So S is all the ordered pairs 1, 1 through 6x, and P, let's just say there's pair die, so P is just 1, 6. So this sample space. Let's make X1. Let X1 be the roll of the first stack. Let X2 be the roll of the second stack. So in other words, X1 of the roll 1, 3 is equal to 1, and X2 of the roll 1, 3 would have been equal to 3. Now, intuitively, we already know that these two random variables are independent. In other words, does knowing the roll of the first die help you know what the second die was? No. There's no useful information you get about the second roll knowing the first roll and vice versa. So intuitively, we know these two things are not related. So they better be independent variables. Makes the third random variable. And let X be the sum of the dice. Or in other words, X of a particular outcome is equal to X1 of that outcome plus X2 of that outcome. Whatever the first dice was plus whatever the second dice was. Okay. So, let X that. So, the two independent variables, maybe as we're going through this example, we should have the definition up here. So, random variables X and Y are independent if and only if the probability of X1 equal to A and probability of X1 equal to A and, not X1, X and Y, and Y equal to B is equal to the probability of X equal to A times the probability of Y equal to B. very similar to what we had independent for events, right? If the probability of x being A and y being B is equal to the probability of x being A times the probability of y being B, then the two random variables are independent. Alright, so let's see if that's the case. I don't know why we need x for this. We'll ignore whatever the author's doing and just think about ourselves. So let's check to see if these two random variables are independent. What is the probability of x1 equaling a particular outcome? A.
1 over 36.
What's the probability of the first die being A? Some number between 1 and 6.
So 1/6.
It's 1/6. What's the probability of x2 being a particular number B? 1/6. What's the probability of x1 being A and y1, not x2, being B? In other words, they're now a particular total rule, right?
Okay. That would be 1/36.
Just 1 over 36. Which is a product of these two things. Hence, they're independent random variables.
Okay.
That make sense?
Yeah.
Okay, so that finishes random variables. Now we move on to calculating expectation. Some intuition for where we might use expectation, or we'll say, I'll probably say expected value over and over again. It means the exact same thing. Expectation, expected value. Let's give you some intuition for it for a second. Let's say you and I are playing a game, and here's the way the game works. I give you a pair of dice, and you get to roll the dice 10 times. Every time you roll the die, whatever the number is, I pay you that amount in dollars. So if you roll a 6, I give you $6. If you roll a 10, I give you $10. You get to play 10 times. How much money do you expect to win playing that game?
There's a range. Could be $10, it could be $103.
Well, there's a lot of things that you could win. How much do you expect to win?
I don't know.
Do you expect to win $1?
Greater than
More than
0.
that.
You expect to win more than $1. So for some reason, you don't just say $1. Do you expect to win $5? You expect more than that. So what's the minimum you can make?
Did you say one die or two?
2 dice.
So the minimum is $2.
You have 10 rolls.
Oh, so yeah, $3.
Here, let me ask the question this way. So let's say we have this game where I let you roll 2 die 10 times.
Okay.
The sum of all your rolls, I pay you that much money.
Feels like
How much money would you be willing to pay to play the game? Maybe that's a better way to think about it. How much money would you be willing to pay me to
20
play that
bucks.
game?
$20.
For sure.
20 bucks? So if I charged you 30 bucks, you wouldn't play? Well, you should.
Yeah, you should.
Well, I guess, but
I don't know.
there wouldn't be any point.
There would be a point. You'd make money.
A median or an average of something.
Probably right in the middle.
Can't believe enough you're coming up with this answer.
Is it?
I was hoping to develop your intuition and then show
The
me
answer
calculate.
yes or no? I'm confused.
How much money should I charge? If I want the game to be fair, how much money should I charge to play this game? Like if I only charge 30 bucks, I'm going to lose money. If I charge 200 bucks, I'm going to make money. Where is it perfectly fair so I know at least how much I need to charge so I'm still making money?
200 and
Yeah, somewhere in between there, but what's the number?
I'm saying right in between.
I just picked 2 random numbers, 20 and 200.
Well, 20 is
That's
20 is the least you can make.
$70.
how much is
70! For the love. 70. You expect to roll a 7. So in 10 tries,
What?
did you do the math and calculate the middle?
I'm sorry.
You did it the hard way, but you got the same number. If I roll 2 dice, the most I expect to roll a 7.
Okay, what do you mean expect?
I mean just that. In terms of how we play that game, I mean I should be charging $70 if I want to, on average, break even.
Right.
Right? Why 70?
Because you have 3
'Cause-
and 4 is share the middle.
If you keep rolling a bunch of numbers, the average of all the numbers you roll is most likely going to be 7, or
Right.
really close to 7.
Right. It's 6 and 1, 5 and 2.
Okay, yeah, I guess
They're all.
it's true too.
They're all 7, but more than that, would be the average of all possible diagrams. So expected value becomes useful when we're talking about questions like that game. So let's do an example with the spinner. So remember we had our spinner, just draw a picture of it. Was 1 was that, 2 was that, 3 and 4, right? Pretend that those proportions are what they're meant to be. And let's say that x is a random variable, it gives a number to whatever you spun. Okay? So what's the probability that x is equal to 1? Just based off of the picture. 1/2, right? And the probability that x is equal to 2, 1/4. The probability that x is equal to 3 is 1/8, and the probability that x is equal to 4 is 1/8. Okay? So now the question might be, if I play this game a ton of times, what would I expect my average value to be if I spin this spinner a ton of times?
Your average, like the value that you might know.
So if I spin this 100 times, and I write out those 100 numbers, and then I average all those numbers, what would I expect that number to be?
2.
Well, let's say I spin it and I get a 1. Okay. I spin it again. This time I get a 2. Spin it again. I get a 1. Spin it again. I get a 3. Spin it again. I get a 1.
So what is your
I get a 1.
question?
I get a 4. So if I spin this spinner a ton of times, 100 times or more,
Okay.
and I average out all those numbers, what would my, well, what's the average of all these numbers? You don't have to take an average, you just sum them up and divide by how many there are.
All right.
So what would I expect that average number to be?
I don't know. That doesn't make any sense.
2.5 is what it feels like, or something like that.
2.5?
Or
Well,
2.
first off, you would expect the number to be closer to 1 than it is to 4,
Yeah.
right?
Yeah.
What if my spinner looked like this? Here's 1, here's 2, here's 3, here's 4. And I spin my spinner a ton of times. Most of the time I'm going to get 1, right?
Okay, that makes sense. How the average would be 1? Makes more sense.
Well, the average won't be 1, it'll be over 1. But it'll be a lot closer to 1 than it is to 4. Okay, so there's some basic sanity checks. The number we expect is closer to 1 than it is to 4. But it's going to be between 1 and 4 for sure, right? It better be. The number we expect better not go against our expectations.
1.5. Two.
Well, we would expect to get a 1/1/2 of the time. I want to
Do 50.
I want to reduce it to that. So let's say we play this 100 times.
Alright.
And let's see what we get. So I would expect to have gotten 1 50 times, right? I would have expected to get 2 25 times. I would have expected to get 3, oh crap,
17.
1/8 of 20 of 100 doesn't work out well. Let's do a number that's divisible by 8. Let's say I spin it 32 times. That way dividing by 8 works nicely.
Okay.
You with me?
Yeah.
So 32, how many times do I expect to get 1?
16.
16 times. How many times do I expect to get 2?
8.
8 times. How many times do I expect to get 3? 4 times. And how many times do I expect to get 4? Also 4 times. And I spun it, how many times? 32. So if I spun it 32 times, this is what I expect my average to be, right? Which is, what does that come out to? 16 plus 16 plus 16 plus 12. Did I do that right? 48 plus 12, 60. Out of 32.
1.875. Which is like what
It's 1
15.
point.
So it's a little less than 2.
So it's 1 and 7/8.
That's what we thought it was.
Yeah, a little bit less than 2 makes sense, right? Between 1 and 2, but close to 2. Yeah, so that makes pretty good sense. Now, we arbitrarily chose 32 times to do this, which is kind of weird, right? I said, if we played the game 32 times, then here's what the average would be, right? What if we played the game 1,000 times? What would the average be? Do we need to go recalculate everything?
Still the same.
No, it would still be the same. It's going to be 1 times, we get 1 1/2 the time, plus
Right.
we get 2 1/4 the time, plus we get 3 1/8 the time, and we would get 4 1/8 the time. And when you add all those up, you should get the exact same thing. This is the expected value that you would get from the spinner. And it came out to whatever it was. Remember what it was?
1/2 plus 1/2 plus.
Yeah, we have a half and a half is 1.
It's 1.875.
And
Which
then
is
another
1
half
7/8.
over there.
1 7/8. So we're saying 15/8.
Yeah.
Divide by 4. Oh, yeah, divide by 4. Top them up. 15/8. So let's make sure that adds up. 8/8 plus 7/8 is 15/8. Yeah. Okay, same thing. So that's the expected value when you play this game, right? Now let's do it for what I said earlier. Let's calculate the expected value of the rolling the 2 dice, and I'll pay you what you make. Ready?
Okay.
So we want to calculate the expected value. That is going to be, maybe we need to write out the probabilities first of each of the things. Maybe that would help us. What's the probability that x is equal to 2?
So it's 1/36.
1/36. And similarly with, let's do it frontwards and backwards as we go. X equal to 12 is 1/36, right?
Yeah.
Now, plus, what's the probability that x is equal to 3? How many ways can you roll a 3?
2.
There's 2 ways to roll a 3. So 1/30, or 2/36, or 1/18. Well, let's just keep it in terms of 36.
Same thing with 11. Right?
Yeah, same thing with 11, but she said wait. The probability, 12. 6, 6 is the only way, 12. 6, 6 is the only way to roll a 12. 1, 1 is the only way to roll a 2. Now we can roll a 1 and a 2, or a 2 and a 1. Or we can roll a 5 and a 6, or a 6 and 5. again, how many ways can we roll a 4?
Oh yeah.
I don't know why I'm saying plus. We're not adding these together, we're just casting them.
3.
There's 3 ways to roll 4.
No.
Yeah.
Oh, wait, yeah. Yeah, there is.
Yeah, there's a 3 and a 1, a 1 and a 3, and a 2 and 2. And similarly with rolling a 10. 6 and 4, 4 and a 6, 5 and 5. Okay? And then the probability that we get a 5 is equal to, how many ways can we get a 5?
I'm gonna randomly just guess here, it's 4.
Are you sure?
Or not.
You can get a 1 and a 4, a 2 and a 3, a 3 and a 2, a 4 and a 1.
4.
And same with the probability of x equaling 9. That's 4 over 36. Probability of x equaling 6 is equal to 5 over 36. Probability of x equaling a 8 is 5 over 36. And probability of x equaling a 7 is 6 over 36. You play the game Settlers?
Yeah.
That's what the dots are on
Yeah,
those.
I know.
They're how many times out of 36 you can expect it to roll.
Right.
Okay. So these are the probabilities of all the different outcomes. Now let's calculate the expected value when you play the game. So the expected value is how many times are you going to get $2? You're going to get $2 1/36 of the time.
Right.
Plus, you're going to get $3 2/36 of the time. Plus, you're going to get $4 3/36 of the time. Plus, you're going to get $5 4/36 of the time. Plus, you're going to get $6 5/36 of the time. Plus, you're going to get $7 6/36 of the time. Plus, you're going to get $8 5/36 of the time. Plus, you're going to get $9 4/36 of the time. Plus $10 3/36 of the time. Plus $11 2/36 of the time. Plus $12 1/36 of the time. Right?
Yeah.
And you add all that up, and it comes out to 70. Did my head real quick.
Okay.
I didn't know. I just thought that's what's getting out. Feel free to check it.
Well, we checked the other way, so it works.
Sketchy? What's sketchy about it? So, if you were to play this game with someone, make sure you charge over $70 for them to play. If you want to make money. If you play enough time, you'll make money.
Probably.
If you play it enough times, you will make money.
Oh, yeah. But you might have to play a billion times before you start making money.
It's true. It's just very unlikely that you have to do that. Okay, so now our definition for expectation. Oh, I didn't specify a real value for any variable. We probably went over this in the last section. So remember what a random variable was. It's a function from S to anything. We call it a real valued random variable if it's a function from S to the real numbers. Does that make sense?
Okay.
The vast majority of the time when we use random variables, we use real random variables.
Right.
It's not very common we don't use real random variables. So, now the expectation for a real random variable. So, let's just write it out. Definition, let SP be a sample space. And let X be a real write as E of x, the expected value of that real random variable, is equal to the sum for all s in S of the probability of getting that times whatever the random variable assigns to that, which is exactly what we did up here. I wrote those backwards for how we did it up here. But x of 1, 1 was 2, and the probability of 1, 1 was 1 over 36. Yeah. Switch these two around so it matches what we did up there. Anything about that definition not make sense?
One second.
Yeah. Match up what we did here with this and see that they're the exact same. Or match it up with what we did to calculate it here. Where do we write this one? Oh, I erased it. So looking up at the spinner, we kind of have two examples up here. Let me arbitrarily. Up here, what was the expected value for the spinner? That was equal to 1 times 1/2 plus 2 times 1/4 plus 3 times 1/8 plus 4 times 1/8, right?
Okay.
That's exactly what this says to do. For each outcome, calculate the sum of the products of the expected value times the probability of it happening. Any questions about that definition? All right, let's just do examples. And start calculating expected values of things. So let SP be the sample space for rolling a single die. And let X be the value of the die.
Is there even any point using x in this case?
Of using X,
Yeah.
the expected, when you're calculating the expected value, you're calculating the expected value of a real random variable. So you need a real random variable X to calculate its expected value.
So, but x of, okay, we're using x
So in this case, our real random variable just assigns the number
to itself.
to, who knows, whatever S is. Maybe S isn't numbers, maybe it's pictures of dice.
Would even then still be mapped to itself, right?
No, it's going to map, so if we make S the pictures of the dice, then X of this would equal 1.
Right.
So whatever our sample space is now, we don't really care about this. X just assigns it the number on the die, and we'll say that P is 1/6 for everything. So each outcome is equally likely. Alright, so what's the expected value of this random variable?
Sorry.
So X is the outcome of the die. So if you roll a 1, X is 1. If you roll a 2, X is 2. What's the expected value of X? Well, if you're stuck already, then
1/6.
it's x of 1 times the probability of 1 plus x of 2 times the probability of 2 plus dot dot dot. Now I'm going to finish writing it. So it's equal to, now give me the numbers. What's x of 1?
1.
Just 1. What's the probability of 1?
6.
1/6. What's x of 2?
2.
Times
3,
1/6. Plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. Now, before even thinking about this math, if you're rolling one die and I ask you what's the expected value, what would you say?
6.
That's the probability of a particular outcome. What's the expected value of your roll? What should I expect you to roll?
Any of them, there's an equal probability.
What should I expect the average of all your rolls to be if you roll a ton of times?
A 4 or 5.
A 4 or 5? What's up with your intuition?
Dude, I don't know.
6-sided die. I can roll a 1 or a 6. Those are equally likely.
Right.
I can roll a 2 or a 4. Those are equally likely. I can roll a 3 or a 5. Those are equally likely.
Yeah.
Oh, whoa, what was I combining? 1, 6, 2, 5, 3, 4. Okay. All those are equally likely.
Okay.
If I roll it a crap ton of times, I average it all out. What do I expect it to be?
3.5.
3.5! All right, 3.5. So this better come out to 3.5 is what our intuition's telling us.
And it does.
And it does. And it comes out to 3.5.
Right.
How do you gamble with you guys?
Yeah, you would win no matter what. Like, I don't. You wouldn't even have to try.
So if you're playing a game with a die, where someone's going to roll the die and you pay them whatever they roll, you need to charge $3.50 to play.
At least.
At least, if you want to make money. And if you got someone over here who thinks 4 or 5, then you go and you just charge them $4 to play, and you make some money. All right, that's the expectation of a die.
What's the use, the purpose of expected value? I'm not getting. Where do you apply it?
Well, for exactly what we just used it for.
Okay.
I mean, that's a really, really simple case. But calculating expected values, and I mean, oh my goodness. What doesn't rely on probability and statistics? It's like everything that we calculate in science, we calculate it as a probability. Everything. There is never something in science that you prove and you say that's true, period. You say, I'm this % confident it's true.
Okay.
So every single scientific phenomenon, when you are, depending on the filter, and you're required to demonstrate that it's true within some margin of error, you have to be this % confident it's true. And those vary off of the fields. So I don't know what exactly the number is for physics, but it's something like 99.99998% sure in order to claim it as true in that field. Whereas if you're in chemistry, you only have to be 99.6% sure. And if you're in biology, you only have to be 95% sure. And if you're in the social sciences, you only have to be 80% sure. The level of assurance we require dictates what field you're in, basically. And so we're much more confident of Einstein's general theory of relativity than we are of any social science phenomenon. The two don't even compare in how sure we are one over the other. It's not even close. But everything in science comes back to, is backed by some model, some probability model. And we said we're this short, so it all comes back to probability statistics. Every scientific phenomena ultimately has to be backed by a mathematical model. to determine those probabilities. Because it is just probabilities. There's no way to say for sure this is the way it is. So, but the simplest place to introduce expected value is, I think the place that brings the most intuition to it is gambling. Alright. Coming up on a proof. Let's do a breakdown and I'll just start writing it up, and then when we come back we'll continue. I think we'll be getting soon to calculating probabilities for, a common one is for stuff like, if you went and took a test that says that you have cancer, what's the odds that you do have cancer? Have we ever done that?
No.
Pretty sure we need to do stuff like that, and so it's got to be in this last section. But it's just everywhere. the expected value of that random variable is the sum of what the real number, the real random variable gives you every time, times the probability of it occurring, right?
This one has space used.
Okay. Working. You good with this? Definition for expected value? The random variable we get times the probability of getting it. That's the expected value, the sum of those. Yeah, no? Do we need to go over that again? Makes sense? Okay, so we have another way of calculating the expected value. And we kind of already did this on the 2 dice roll. So let SP be a sample space and let X be a real valued random variable. Then the expected value is equal to the sum across all real numbers times the probability of the expected value giving you that real number. Now this seems crazy. We're summing across all real numbers, every real number. How many real numbers are there?
There's a lot.
A lot, a little bit more than that, but yeah, close. So we're summing across all real numbers and we're multiplying it times the probability of the expected value being that real number. Now for most real numbers, the probability of X being that real number is going to be
Really small.
0. It's going to be 0.
Why?
Let's go to the case where we're talking about rolling 2 dice. Okay? And X is the sum of those 2 dice. What about when age 26 billion? How many times is X going to be 26 billion? It's not. Most of the time, X is going to be on a finite set S, so it's going to have a finite number of numbers.
Okay.
And so for infinitely many values A, that's just going to be 0. Okay? So most of the time, this is 0. But we're doing 0 times a lot of numbers. And then we only care about the A's when we actually get a value here. You with me? Okay, so it might seem kind of weird that we do this at first, but hopefully it helps normalize your thinking, knowing that this is 0 the vast majority of the time. Okay, so we're going to prove that this and this actually give you the same thing, and you can think about it either way. That's what we're proving here. Understand what we're proving? And it's starting to make more sense that this isn't too crazy.
Wait, what? No, what are we proving?
We're proving that the expected value
Oh.
is equal to this.
Okay.
So we already know that this is the expected value. We're proving that this is another way to calculate the expected value.
Okay.
With me? Okay, so first off, what's the expected value? As we already have it, it's just this exactly. Right? That's just flat out plugging in the definition of expected value. Now, what we're going to do, this is a sum, right? We're going to break the sum down. We're going to collect all the terms in the sum that give us a common value for xx.
Bye.
See ya. So for example, when we're talking about rolling 2 dice, 1, 2, x of 1, 2, and x of 2, 1, both give us 3. Right? That's equal to 3, and that's equal to 3 when x was the sum of what we rolled. So what I'm saying here is, I want to collect all the excesses together that give me the same real number, 3. You with me?
Oh, yeah.
Okay. What's another? Trying to think of a small example I could write out everything for explicitly on the side to do this as we go.
It's like you're
2 dice is kind of a lot.
Yeah. We could do a 4-sided die.
Yeah, let's explicitly write out a 4-sided die. So S is equal to 1, 2, 3, 4. Now we'll make probability of each individual outcome just 1/4. Oh, sorry, it's equal to that squared. So the probability of each individual outcome is 16. Let's go to 3 only. Make it 1/9. Keep things usable. And let's say that x, which is from S to R, is the function for 1, 1, it gives us 1, 9. Or sorry, for 1, 1 it gives us 2. It gives us the outcome of each roll, right? And then we could have rolled a 1, 2, in which case x gives us a 3. We could have rolled whatever we could have rolled all the way up to. We could have rolled our highest roll is going to be a 3, 3. In which case x gives us a 6. You with me on our random variable? For each roll, it assigns the sum of the roll. For each roll, it assigns the sum of the roll. And we're just rolling 2 3-sided die, which I know doesn't exist, but we'll let it be. Actually, you can make it 2-sided die.
It was curved, right?
You can actually make a fair 3-sided die. It's one of the proofs I did when I was in school, but you have a cylinder. And there actually comes a point that if I keep cutting the cylinder, there comes a point where it's actually fair. It has just as much probability as landing on one of these two faces as it does as landing on the side of the cylinder. So I can eventually make a cylinder short enough that has just as likely a chance of landing on one of its two top bottom faces as it does of landing on a side.
Okay.
Right? Because think about a coin. A coin is a really short cylinder. It never lands on a side. Think about a really long cylinder. It's always going to land on the side. There's got to be some point in between where it's equal. So we've got one of these weird cylinders. Where it's just as likely to land on one of the two curved faces as it is on the top one. Okay. And here's our real variable, our real random variable x. The expected value of x is equal to, and we're going to maybe come over here some so that we have as much room as we need. The expected value of x is equal to x of 1, 1 times the probability of 1, 1 plus x of 1, 2 times the probability of okay, I'm not going to write my inner. Okay, here's how I'm going to write it. And I know it's going to be weird, but it's going to help me write. I'm going to do 1, 1 like that. So x of 1, 1, probability of 1, 1, plus x of 1, 2, probability of 1, 2, plus x of 1, 3, probability of 1, 3, plus x of 1, oh, we're done with the ones. Let's go to the new line and follow the pattern. Plus x of 2, 1, probability of 2, 1, plus x of 2, 2, probability of 2, 2, plus x of 2, 3, probability of 2, 3, plus x of 3, 1, probability of 3, 1, plus x of 3, 2, probability of 3, 2, plus x of 3, 3, probability of 3, 3. All right, writing everything out explicitly, there's our expected value, right? Right. And now, rewriting this exact thing,
X is just the
x
sum.
of 1, 1 is, yeah, it's just a sum. So this is going to be 2 times,
1 over 36.
well, we need to keep this in this format to follow what I'm doing over there. So, plus 3 times probability of 1, 2, plus 4 times probability of, 4 times the probability of 1, 3, plus 3 times the probability of 2, 1, plus 4 times the probability of
probability of 2, 2 plus 5 times the probability of 2, 3 plus that right here, 4 times the probability of 3, 1 plus 5 times the probability of 3, 2 plus 6 times the probability of 3, 3. Who knows? Maybe it's fair, maybe it's not. Let's not pretend it's fair. Let's pretend we don't know. Probability is whatever the probability is. Maybe it's fair, maybe it's not. We got some weird cylinder, right? The point is, here's the expected value, right?
Okay.
You with me so far?
Yeah.
Now notice, 3 came up here, 3 came up here, 4 came up here, 4 came up here, 5 came up here, 5 came up here. We have repeating values for x of s.
There's another 4.
The point is duplicate, right? So what I'm saying I can do here is I can take this sum, which is this sum right here, and I can rewrite it so that I view it as smaller sums, where the smaller sums are grouped together based off of what this value gave. So now I'm going to rewrite it as this is equal to, let's see, our first sum is going to be where a is 2. Maybe I'll do like a bracket like this. We have 2 times the probability of 1, 1. That's the only case where 2 is leading, right? Plus 3, let's see, 3 has a probability of 1, 2, plus 3 times the probability of 2, 1, that's all our 3's, plus 4, we have the probability of 1, 3, plus 4 times the probability of 2, 2, plus 4 times the probability of 3, 1, plus 5 probability to 3 plus 5 probability of 3, 2 plus 6 probability of 3, 3. Okay, so that's exactly what I'm doing right here. I'm saying everywhere where all my x of s's gave the same value, I can group those together into inner sums. This is the sum of all the ones where x of s equaled 2. This is the sum of all the ones where x of s equaled 3. This is where all the x of s equal 4. This is where they all equal 5. This is where they all equal 6. And this is where they all equal numbers that weren't those. With me? That's exactly what we're doing here. We're saying collect all the terms that give a common value for x of s, and we get this. So sum up for all the real numbers, and then in our inner sums, in our brackets, same way I have the brackets right here, we do a sum for all the s's in S, in big S, where x of s equaled that particular value a. So when a was 2, here they all are. When a was 3, here they all are. When a was 4, here they all are. When a was 5, here they all are. When a was 6, here they all are. When a was anything else, it was always 0, so we didn't even bother writing it. You with me? Kind of? You know what that?
Well, I see what you're saying. I'm not really
The expected value equals a sum. For each real number, we can calculate an inner sum of all the terms that had x of s equal to a.
Okay. Yeah.
So pick a real number, any real number.
40.
40. Here's all the ones where they were equal to 40. Pick another real number.
20.
20. Yeah, those were also right here.
Yeah.
But eventually you're going to say 2, 3, 4, 5, and 6. Here's the ones for those numbers. Here's the ones for all the other numbers. Right?
And I'd have a bunch of pluses for every other real number of just empty brackets. That's what I'm doing here. So for each real number A, group the terms together that gave an A here. Do an inner sum of all the ones that gave that A value
Okay.
for x of s.
All right.
Is that clicking?
Well, yeah, that makes sense. I'm not sure where we're going with it.
Oh, well, you'll see where we go with it. So, are you good with this sum? Once you wrap your head around this, the rest just falls into place, I think.
Okay, so that's saying that.
The sum for all real numbers,
Okay, right.
inner sum, all the x of s's times p sub s's that gave A for x of s.
Okay. Okay.
For every real number, add up all the x of s's times p sub s's that gave A for x of s. And do that for every real number. And we calculated all of them. Is that clicking? Okay, so if you understand this, then what is x of s always going to be in this case? It's going to be whatever that A was, right?
Right.
So all I'm going to do is get rid of that x of s with an A. That's all we've done so far. So for every real number A, add up all the x of s's that gave you an A times their probability. And you just add all those up. Good? Now, the sum times a constant. If I have a constant in every term, the next thing I'm doing is I'm taking these and I'm saying, in this I can factor out 2, this I can factor out 3, this I can factor out 4, this I can factor out 5, this I can factor out 6. Saying in each of these terms, now I can factor out A. With me?
Yeah.
Okay. So now, what am I adding up in here? I'm adding up all the probabilities where x of s gave me A, right?
So.
I'm adding up all the probabilities where my real variable gave me A, where my random variable gave me A, right?
I want to take one more step back.
Up here?
I see what you did. You factored it out, but why is it written like that? I'm not sure how we got.
I pulled it out of the inner sum.
Okay. All right. Yeah.
Oh, you're saying you want it like this?
No, that works fine. Either way, I guess it's the same thing. Okay.
All right. So you're good from here to here. So now we're saying the sum of all the probabilities where our random variable equaled A. That is exactly the probability that our random variable equals A. It's the sum of all the probabilities where the random variable gave you A.
Times A.
Well, I'm saying this sum right here is this. That's what we mean by this. What do we mean by the probability that x equals A? We mean the sum of all the probabilities
Right.
where the real variable was A. Or the random variable was A. That's what this means. It means this sum.
Right.
Right? So when I said the probability that x equals 5 in this context, that's this probability plus this probability. So let me write this long thing out one more time over here, doing everything that we're doing. So now we're saying factor out the 2. That's 2 times the probability that x is equal to 2, plus 3 times the probability that x is equal to 3, plus 4 times the probability that x is equal to 4, plus 5 times the probability that x is equal to 5, plus 6 times the probability that x is equal to 6. Right? The probability that we get a 2 or a 3, plus the probability that we get a 3 or 2, is a probability that x equals 5. That's what it is. It's the sum of those two things. If I ask you to calculate what's the probability of a 5, you say, well, what's the probability of rolling a 2 and a 3? And what's the probability of rolling a 3 and 2 and add them together? That's the probability of rolling a 5. So you see how this inner sum is exactly the probability of the random variable being that.
Yeah.
I know that this is a lot of notation. The reason I want to explicitly go through it all is because hopefully it's helping you click in your mind, okay, what exactly this function is, and hopefully helping you get more comfortable with sums. So in short, we're saying that this sum right here is the same thing as this sum right here. That's what we were proving. And this is it in general. Any questions? You just look out for a sec. Okay, so, good, can I erase? Ready to continue? Or maybe I'll just come over here, leave that up for a bit. So, now the question is going to be, can we calculate expected values from expected values? So, for example, if I know that the expected value of x, whatever it is equal to a third, and I know that the expected value of some other random variable of y is equal to, I don't know, 6.7, is it possible for me to, just from that information, calculate the expected value of x plus y? Is it possible for me to calculate the expected value of x times y? If so, how do we do those things? You understand what I'm saying?
What? Can you give me an example of what x plus y would be?
No, that would make sense with those numbers because those were so random. But x could be the outcome of the first die, y could be the outcome of the second die. So if we know the expected value from rolling the first die, if we know the expected value from rolling the second die, can we calculate the expected value of rolling both die?
Okay.
Right? So let's think about it that way. So let's say x is rolling the first die, 6-sided die, go back to 6 instead of 4. What's the expected value of rolling one die?
3.5.
3.5. What's the expected value of rolling the other die?
Also
3.5. Is it true that the expected value of the sum of two dice is going to be 7?
Yeah.
Yeah, in that case it's true. Is it true that the expected value of the product of the two numbers on the die would be, I don't know, what does that come out to? Whatever it comes out to, 3.5 squared? That was not as obvious.
But probably.
But probably, if we wrote out the product of the two dice, would it come out to that? And did we just get lucky when we did this? Does this always work?
Yeah.
These are the questions that we're going to answer, right? So, now does that make sense?
Okay.
So let's answer those questions. First off, this one's really easy. Prove, I'm not going to write out everything, I'm going to use words for a lot of it. Prove that if x and y are expected values on some sample space SP, prove that the expected value of x plus the expected value of y is equal to the expected value of x plus y. Right? Assuming we have some sample space, and these are real random variables, prove that the sum of the expected values is the expected value of the sum. With me? Okay. 1, let z equal x plus y. Now that's kind of weird, so let's make sure that we understand how to add functions together. Remember, these are functions.
Yeah, that's right.
What do we mean when we say f of x plus g of x?
You just write out what they are, right?
It's just their flat out sum of things. Just make sure you keep in mind that these are functions. So if I say h equals f plus g, what I mean is h of x is equal to whatever value you get when you plug in x into f, and plus whatever value you get when you plug x into g, right? So that's all we mean by the sum. But just remember we're talking about functions. So let z be the sum of those two real random variables. Okay? The expected value of z then, z, is equal to the sum for, remember, pretend we have some sample space, so for all s in s, it's going to be z of s times the probability of that s, right?
Right.
Which is going to equal the sum for all s, little s in s, of x of s plus y of s times p of s What is z of s? It's the sum of those two things. Just like what's h of x? It's f of x plus g of x. That's what we mean by h of x, when we define h to be the sum of two functions. Okay? Which, if we distribute that p of s in, remember this is a sum. Maybe you're not as used to this notation. I'm saying we're summing up these. The sum, we're plugging in s to each of these. Sorry, does it make sense that what this applies to? We're summing up all here. I don't want to put parentheses there. I just don't know how comfortable you are with this. In other words, I can't factor out the p of s. That doesn't make sense.
Yeah, we kind of getting the whole time. It's just the new notation of random variables and that sort of thing. Because what is kind of just throwing off everything I'm used to is because I'm not used to using functions in that way.
Yeah, it's a different way of using functions. Just
That's just kind of confusing.
using them like this, it's weird the first time you come across it.
So I'm thinking random variables and the idea itself kind of makes sense, but then the notation that you use and kind of how it works, we're using summations of functions, and that's just kind of messing.
Summations of the value the function gives you
Right.
for each input.
Right.
Right? Okay? So now I'm going to distribute this p of s to each of those. So that's equal to the sum for all s in big S of, well, I'll keep that parenthesis there just in case it's confusing. P of s times x of s. Well, right the other way. Yes. X of s times p of s plus y of s times p of s. Right?
Okay.
Distributing it in. And then finally, I can just break this into two separate sums. Is equal to the sum s in s of x of s, p of s, plus the sum for all s and big S of y of s, p of s. Right? Since we're just adding anyways, instead of doing the sum of this plus this, I can do the sum of all these plus the sum of all these.
Oh, you're distributing the sum, kind of?
I'm splitting my sum into two separate sums. Okay, let's do something similar, one that we know. Let's say I'm doing the sum for k equals 1 to 5 of k plus 2k. You with me?
Yeah.
I'm rewriting this as the sum k equals 1 to 5 of k plus the sum k equals 1 to 5 of 2k.
Okay.
Because in the end, this is just a big sum, right?
Yeah.
So I'm saying I'm going to do all these terms first and then all these terms. Instead of doing this and this for 1, and this for 2, and then this and this for 3. I'm going to do this for 1 through 5 and then this for 1 through 5.
Okay.
Is it clicking?
Yeah.
I mean, this to this should not be a weird step. So if this to this is a weird step, we're not comfortable with sums.
Well, yeah, well, this is the class where I basically use, so I've never done that before, so that makes sense now, but I've never done that before.
We didn't do that in proof by induction, like all the time.
Well, we use sums all the time, that's where I got comfortable with sums, but I don't remember splitting it up like that.
You were the one that was always doing proof by smallest counterexample. So that's why you didn't do it a lot. Okay.
Well, even on proof by induction, I don't remember doing that, and I did the proof by induction lesson where all the homework was induction.
So you often use sums in proof by induction. So you would have like,
Right, I remember. Yeah, you use them all the time.
but you split the sums all the time. Well, you didn't split the sum, you pulled a term out of the sum is what we did all the time. Not splitting the sums, I guess. But nonetheless, splitting a sum from this to this should be pretty intuitive.
Okay.
And that's exactly what we're doing here. Instead of summing them like that, we're summing them like that. And then finally, obviously, what is this?
That's the
That's the expected value of x.
correct.
Which is exactly what we were trying to prove.
Yep. All right, that's cool.
So now, let's do the product. Oh, the constant. I don't know, we need to do the constant. The next thing they do is prove that the expected value of x times some real number c is equal to the expected value of cx, like that. In other words, this gives us a sum. Take your sum and multiply it by c is the same thing as having c applied to each term in your sum and adding it up.
Okay. Yeah.
Because this is just a sum, right?
That makes pretty good sense.
So a constant times your sum is the same thing as your sum with the constant included in each term. This is a factored out version of this. That make sense? And then finally, we have what's called the linearity of expectation, which is combining this and this into one. So maybe I'll just write it right here.
the same way they do. The expected value of A is just a constant, times a function, the output of the function, plus B times Y is equal to A times the expected value of X plus B times the expected value of Y, combining those two. And that's called linearity.
Linear what?
Linearity. It's a common property that functions have. What's an obvious example? I swear we've come across this already. I can't remember the context. Linearity of I don't know why I can't come up with an example off the top of my head, especially because it comes up all over the place. And he doesn't mention an example where he's brought up before. Maybe I'm thinking of calculus that came up and it hasn't come up here yet. No, linear algebra. So you don't know what a linear transformation is in general. Transformation of the coordinates.
In like cost algebra terms or algebra 2 terms.
Well, every matrix represents a linear transformation. And matrix multiplication follows this for a vector.
I guess I'm out here.
Yeah, so if we're doing some matrix multiplication, if these were vectors, these were real numbers, and this was a matrix multiplication, then this would be this.
I don't know what a vector is in algebra.
But you know what a matrix is?
Yeah.
Vector is, you can think about it as just I mean, the exact definition of a vector is it's a member of a vector space, which is kind of, you have to know what vector space is to really know what a vector is. But an intuitive way to think about it is it's a vector with width 1, height, whatever. Could be a vector. So it can have as many real numbers as you want, but it's all in one column. We call that a column vector, or if it's all in one row, then we would also have a row vector. It's not a good way to define a vector because a vector, by definition, is a member of a vector space. You need to know what a vector space is. So, never mind. Forget about that. I can't come up with an example that we would use for that. But linearity is something that comes up in math all the time. Things that preserve linearity, that have the property of linearity, come up over and over again. And it's really nice when you do. So expectation follows that. Let x be a 0, 1 random variable. 0, 1 random variable. Oh. So, here's turn that off. A 0, 1 random variable then is a random variable x whose outputs are either 0 or 1. That's all the output. Okay? So a random, we can think about that as like a success failure one. 1 if it was a success, 0 if it was a failure. So maybe we set up a game where you win if you flip a heads, you lose if you don't. So it's either success or failure each time you do it, right? So we could create a random variable that gives you 1 if you flip heads, 0 if you don't. And that would be what we call a 1, 0 random variable. And then it's real nice to calculate the expected values of 1, 0 random variables because if x is a 0, 1 random variable, equal just the probability that x is equal to 1. Why does it equal this? Well, let's write out its definition explicitly. That's going to be the probability that x is equal to 0 times 0 plus the probability that x is going to equal 1 times 1, right? If my random variable can only spit out ones and zeros.
Okay.
I mean, let's make real intuitive sense of it real quick with a game.
Yeah, that makes sense.
You're flipping a coin. You get $1 if you win. You don't get $1 if you. Sorry. Get $1 if you win. Flipping a coin, you get $1 if you flip heads. What's your expected value point in the game?
0.5.
50 cents, right? That's what you expect. So we would expect this to come out 0.5, which is the probability of you flipping a heads or getting $1. Or we can say that's the probability of you flipping a tails times 0 plus probability of you flipping a heads times 1. So they're really easy. You guys are just dead.
I'm trying to just grasp it, all of it. It's hard, I don't know why, it's challenging to take.
We still got a good amount of the section to go through.
Maybe I just need a more intuitive sense of what our expected value. I don't know.
Now, I already scheduled with Brigham, so I can't push back a day. Okay. Well, no point in continuing if you guys aren't following.
Like, it makes sense, just not a lot. Like,
Okay.
it doesn't really, like, just fit. It doesn't.
So here's what we're going to do, because I feel like you're burned out. Am I right?
No, I'm just struggling. Like, I can still try. I mean, I'm just not getting it. Every time I see something, I'm like, okay, what does that mean? Okay, what does that mean? And then go back.
Okay. So here's what we'll do. We'll read the section. This section, read it. Just read it.
Okay.
Come back next time. Maybe I'll recap the whole section from beginning to end to try and get everything in one go.
Recap the whole section or the whole chapter?
Section. I'll recap the chapter, but I mean recover the whole section, going over each thing explicitly. And then I guess we'll just do the test a week after I do the special relativity thing. Because I can't change that. I already committed to it.
Okay.
So we're going to have like a weird break. So you guys are going to have tons of time to study for the test on this.
Okay.
Does that make sense?
Yeah. I was getting comfortable with the rest of it, but like everything up to today, I was getting pretty okay with.
So maybe doing the section on random variables will help you, because we did the section on random variables. That one was really small. So do the homework for that. Maybe that will help all of this start sinking in. Get as far on the expected value homework as you can. Make sure you read the section. And then hopefully when you come back, we can just knock it out of the park. Because we're not asking any real probability questions until we have you start calculating expected values. So chances are the vast majority of everything on the test is going to be like expected values. Because that's what you calculate probabilities for. So I really want you to understand that. That's what we've been leading up to is expected value. So if that's not clicking, let's hit the brakes, wrap our heads around all this.
I feel like it would have been almost more useful to do random variables last week and have some time.
Maybe.
And then so when you get hit with this week, you've had some time to work with random variables and let us see.
I need to rework out my schedule because, yeah, we had it weird for this chapter. The first week we were like, we're already done.
Yeah, those. Yeah.
Yeah, we could have added another section onto that, shoved random variables onto last week, and then spent the whole time class today doing expected value.
Yeah.
And I could have even introduced expected value last time too. like the intuition, the idea of what I brought up at the beginning of rolling 2 dice. So we'll start there. Start your homework for expected value. Let's get as far as we can.